Hello, this is lecture 7.2 of the GPU teaching kit. We'll be introducing data races. The objective of this lecture is to understand data races in parallel computing. We'll learn that data races can occur when performing read, modify, write operations, and these data races can cause errors that are hard to reproduce. We will then learn that atomic operations are designed to eliminate such data races. This slide reviews the first iteration of the thread execution in our text histogram example. We see that all the threads will be reading the first character of their input partition and increment the appropriate pin counter value. This is done by reading the original pin counter value, add 1 to it, and write back into that location. So this is referred to as a read, modify, write operation. And we see that thread 0 and thread 2 both want to increment the bin counter value for M through P. And the outcome of the iteration should reflect the work done by both thread 0 and thread 2, and the value should be 2. Read, modify, write operations are used in many real-life collaboration patterns. For example, we can have multiple bank tellers to count the total amount of cash in the safe. Each one of them will grab a pile of cash and count. And we can maintain a central display of the running total. Whenever someone finishes counting a pile, the person can read the current running total, which is a read operation, and add the subtotal of the pile into the running total, which is modify and write. In this example, a bad outcome would be that some of the piles were not accounted for in the final total. Read, modify, write operations are also used in a common parallel service pattern. For example, we can have multiple customer service agents to serve waiting customers. The system maintains two numbers, the number to be given to the next incoming customer, and we call this number I, and the number for the customer to be served next, and we call this number S. The system gives each incoming customer a number, which is read operation on I, and increments the number to be given to the next customer by 1. This is modify write operation on I. A central display will show the number for the customer to be served next. When an agent becomes available, he or she calls the number, which is a read operation on S, and increments the display number by 1, which is a modify write operation on S. In this pattern, there are two bad outcomes. One is if multiple customers receive the same number and only one of them receives service. And the second bad outcome would be that multiple agents serve the same number and only one of them will get a customer. Read, modify, write operations are also used in a common arbitration pattern. For example, we may have multiple customers booking airline tickets in parallel. Each customer will bring up a flight seat map, which is a read on the seat status, and he or she would decide on a seat and then update the seat map and mark the selected seat as taken. So this is modify write to the seat status. A bad outcome of this example is if multiple passengers ended up booking the same seat. During boarding time, only one of them can get to sit in that seat. Now we're ready to study the root cause of bad outcomes in all the previous examples. Here we present a simple representative example where two threads both attempt to perform a read, modify, write operation on the same memory location X. We assume that old and new are per thread register variables. So thread 1 will have its own version of old and new, and thread 2 will also have its own version of old and new. In each case, the thread will attempt to load the old value from memory location X, add 1 to it, and write the new value into the memory location X. There are two important questions about the outcome of this piece of code. One is, if the memory location value was initially 0, what would be the value of memory location X be after threads 1 and thread 2 have completed? If the answer is 2, it's a good outcome. If the answer is other than 2, it's a bad outcome. The second question is, what does each thread get in their old variable? If one thread gets a value 0 and the other thread gets a value 1, it's a good outcome. It doesn't matter which one gets which. However, if both threads get a value 0 or both threads get a value 1, then we have a bad outcome. Unfortunately, the answers to these questions could vary according to the relative execution timing between the two threads, which is referred to as a data race. In the next 4 slides, we will show the potential timing scenarios between the execution of thread 1 and the execution of thread 2. In scenario 1, thread 1 will complete its read, modify, write sequence before thread 2 starts its sequence. At time 1, thread 1 will load the initial value of memory location X into the O variable, and it will write 0 into the O variable. In time 2, thread 1 will add 1 to the O variable value and write value 1 into the new variable. And at time 3, thread 1 will write the new variable value, which is 1, into the memory location X. At time 4, thread 2 will load the value from memory location X into the old variable, and the value will be 1. And at time 5, thread 2 will add 1 to the old variable value and write value 2 into the new variable. At time 6, thread 2 will write the new variable value 2 into memory location X. So after the execution of the entire sequence, thread 1's old variable value will be 0, thread 2's old variable value will be 1, and the value in the memory location X will be 2. And this is a good outcome. In timing scenario 2, thread 2 will execute its read, modify, write sequence before thread 1 starts its sequence. And the role of thread 1 and thread 2 will be reversed from the previous scenario. So it's easy to see that thread 1's old variable value will be 1, thread 2's old variable value will be 0, and the final value of the memory location X will be 2 after this scenario. And this is also a good outcome. In scenario 3, thread 1 begins its read, modify, write sequence before thread 2. However, thread 1 did not have the chance to complete its sequence before thread 2 starts its sequence. So thread 2 loads the memory location X into its old value before thread 1 has the chance to write its new value into memory location X. As a result, both thread 1 and thread 2 have 0 in their old variable, and after the sequence, the memory location X value is 1. and this is a bad outcome. Scenario 4, thread 2 starts its read modify sequence before thread 1, but thread 1 initiates its read modify write sequence before thread 2 has the chance to complete its sequence. So now thread 1 and thread 2 both will have 0 value in their old variable, and memory location X will have a value 1 after the sequence. This is also a bad outcome. This leads us to the purpose of atomic operations. The atomic operations are designed to ensure good outcomes when threads perform read, modify, write operations on the same memory location. For our example, we want to ensure that if thread 1 starts its read, modify, write operation, its sequence will be complete before thread 2 can start its sequence. Or if thread 2 starts its read, modify, write operation before thread 1, it will complete its read, modify, write sequence before thread 1 starts its sequence. And this is the reason why it's called atomic operations. The atomic operations are read, modify, write operations where the entire sequence will be executed in an atomic manner, and no other read, modify, write operations to the same location will be allowed to overlap with that sequence. This completes lecture 7.2 of the GPU teaching kit. Thank you.